All right, thank you so much, Tim. Good morning, everyone. Welcome to the second installment of the Multi-Fidelity tutorial. For those of you who are not here yesterday, I think the YouTube video is already available, so I invite you to have a look. I will give a very brief overview. In the interest of time, you see we still have a few slides left. This is where we left off things, and this is a summary of what was the major part of the discussion yesterday, which was focused on multi-fidelity methods for sampling, and more specifically for uncertainty propagation, where the goal was to estimate mean values using Monte Carlo estimators. And we revisited the idea of a standard Monte Carlo estimation. We saw the strengths and limitations of that, and then how multi-fidelity methods, where hierarchies of low and high fidelity models are used, can be exploited to reduce the variance of standard Monte Carlo estimation. And the picture, so to summarize this in one picture, is shown here. So we have a high fidelity model that we assume we trust gives us the right prediction, so the right prediction for the quantity of interest. We have low fidelity models that are less accurate, but ideally much cheaper to evaluate. In the multi-fidelity method, instead of leveraging one or the other, as is typically done in standard methods, we want to use all of them. In the context of Monte Carlo sampling, this means that we use Monte Carlo estimators that depend on both high and low fidelity models. This is the way the multi-fidelity idea manifests here. And because we keep the high fidelity model in the loop, we can guarantee that the estimator is unbiased, which is desirable. And we use the low fidelity models for variance reduction and speedups. So in general, if we have decent low fidelity models, most of the effort will be put onto them, whereas the high fidelity model will be queried just a reduced number of times, which is what we want. And as a reminder, so this is the formula that we got for the variance of the multi-fidelity Monte Carlo estimator, depending on k low fidelity models, where we have a product between the variance of the single model Monte Carlo estimator multiplied with an expression that depends on correlation coefficients and evaluation costs. So these two quantities are the most important quantities that identify low fidelity models in multi-fidelity Monte Carlo settings. And then we said that, this expression has some meaning. It also indicates that low fidelity models should not be assessed in isolation, but rather, their impact is directly measured in the way they interact with the other models in the hierarchy. All right, so let's see two examples to build intuition about what this means. And in these examples, what I will do, I will use the analytical formula for the mean squared error, so the expression that we've just seen, in two settings. So in both settings, we will have up to 4 models in total, meaning the high fidelity model and 3 low fidelity models. And the goal of this is to convey a few important things about multi-fidelity Monte Carlo sampling. All right, so first let's consider a setup where we have 3 heterogeneous low fidelity models. What do I mean by this? I don't care per se what those models are, but what I care about is their correlation coefficients with the high fidelity model and their relative evaluation costs, so the speed up that we get with using these low fidelity models. And such situations arise, for example, when combining things like reduced physics models with cheap data-driven surrogates that may not be very accurate on their own. So this is a realistic setting that can happen. So as I said, I'm just using the formula here. So I made up some numbers to convey some points here. And let's say for simplicity that I fix the variance of the high fidelity model to 1. And as we discussed last time, we normalize the costs such that the cost of the high fidelity model is 1 and everything else is relative to that. So let's assume that we have now a bi-fidelity multi-fidelity Monte Carlo estimator, where in addition to the high fidelity model, we have one low fidelity model that has a high correlation coefficient, so this is 0.999, but it gives us a speed up of only 2, so the relative cost is 0.5. As we observe in this plot, so comparing the theoretical estimate for the mean squared error of the standard Monte Carlo estimator that uses just the high-fidelity model and the high-fidelity Monte Carlo estimator, we get variance reduction because of the low-fidelity model. Not a lot, because even though the correlation coefficient is large, the speed up is not tremendous. Let's say we add a second low-fidelity model into the mix, less accurate from the point of view of correlation coefficient, but this model gives more speed up. So this is 10 times faster to evaluate than the high-fidelity model. So we see that we get quite a substantial decrease in the mean squared error, or decrease in the variance, essentially, because the rate is the same. And now let's say we add a third model, so less accurate than the first two. So this forms the model hierarchy. So it has a correlation coefficient of 0.96, but it is 100 times faster to evaluate. So what we notice is that when we add this third model, so now we have a multi-fidelity Monte Carlo estimator with the high-fidelity model and 3 low-fidelity models, we get more substantial variance reduction. So this is to say in this setting, so what do I mean by heterogeneous models? They have, we have models with high correlation coefficients, but that are more expensive to evaluate, and models that are less accurate from the point of view of correlation coefficient, but they are a lot cheaper to evaluate. So this, tells us that, this model maybe in reality you'll not trust it to give, predictions that can replace the high fidelity model predictions. It's still pretty decent, but, together with the other models in a multi-fidelity hierarchy can give rise to substantial speedups, substantial variance reduction. Now let's consider again a setting with, like we did now, where I will keep the correlation coefficients identical to this example, but now I'm considering the setting where low-fidelity models provide substantial speedups, more substantial than before. And this is, so the intuition is generally that if I have a problem that is computationally more expensive, it is in general more difficult to use low-fidelity models or get more, gains from using low-fidelity models. It turns out that in multi-fidelity methods, however, if you manage to get models, low-fidelity models that have relatively high correlation coefficients, you can actually get even more improvements. Because if the speed up is more substantial, then this will decrease the mean squared error even more. And another point I want to convey is that if you are using this method and you have a very good low fidelity model, meaning with high correlation coefficient and substantial speed up, you may not gain anything else by introducing other methods into the hierarchy, because that model on its own will reduce the variance quite substantially. All right, so such situations, of course, arise when we have, as I said, an accurate and cheap, in general, data-driven surrogate model, because data-driven surrogates, as we know, usually provide the most speed up. Yes?
Sorry, this reminds me of a quick question. So sometimes we build a neural network as a cheap surrogate, and that's a data-driven one.
Yes.
But because of the training, actually, certain area, certain region of the design space or the input, we are more confident, and a certain area we are maybe not be that confident, especially when the input space is high dimensional, like all the points are kind of far away to each other. So in that case, how do you quantify the correlation?
So the correlation
with your high fidelity model, because I mean, like, it's a global concept, or it's kind of because I think some areas correlation going to be really bad, right? Like my prediction might not be that reliable because it's kind of generalization, not good. So how is this going to be taken into consideration in your modeling? Because in the training set, I believe the correlation is going to be very good, but when we try to generalize to some data points we never seen in the training set, the correlation are hard to. I mean, there might not be enough guarantee to have very good correlation. But overall, how much?
So we don't need a guarantee in this setting. That's the beauty. We just need correlation coefficients. So if what your network predicts, so it will be a quantity of interest. If that is highly correlated with that of the high fidelity model, doesn't really matter whether your network is locally inaccurate in certain regions in the domain. So what really matters is that it gives correlated predictions.
But this is kind of like assumption, or because we don't know what is the true correlation, right? Because if we don't go through the whole input space, the
This is something that you have to estimate. So this algorithm needs this. I will have a slide about what the algorithm needs. But yes, you need to estimate this. And of course, you don't have the actual number. You need a Monte Carlo estimator. Yes.
And if you estimate, to follow on, if you estimate the correlation coefficient wrong, it just converges slower, right? It's not like it fails.
So if you estimate it wrong, meaning that you have an inaccurate estimate, ideally you don't have a mistake in your code, you're just using the right formula with the wrong samples. So we'll plug those numbers into the algorithm. The algorithm will give you a certain model management strategy. It will say, you have to evaluate this model this number of times. You may not get the optimal result. So it's kind of up to you when you use this method to ensure that you sample the input space in the right place to estimate the correlation coefficients.
When you say optimal result, do you mean it will have a higher variance, or like it will be
It will likely have a higher variance.
It won't be biased still, right?
It will not be biased, no.
It's just...
Yeah, so as long as you evaluate the high-fidelity model at least once, it will not be biased. Yes?
In this, you're assuming that the low-fidelity models have no bias?
So low-fidelity models, so we discussed about this yesterday, they will have a bias. But that bias will not manifest in the multi-fidelity Monte Carlo estimator, because as long as we keep the high-fidelity model in the estimator, we can guarantee that we'll have an unbiased overall estimator. So the low-fidelity models will have a bias with respect to the high-fidelity model, but if we put all of them together, we'll not have a bias. And that's actually quite, opens the door to models that are not necessarily very accurate on their own, but can be useful in this setting. All right, so now we have the same situation as before, but now we start with a model that is 10,000 times cheaper to evaluate, which is often the case in data-driven modeling. Actually, if you have a very expensive high-fidelity simulation, this will probably be billions of times faster to evaluate. So what we see is that we get more substantial variance reduction. So it's roughly 4 orders of magnitude or more, because the model has a high correlation coefficient and also provides substantial reduction. Now let's add the second model into the loop. So the same correlation coefficient as the previous experiment, and this time, this second low-fidelity model, I assume is 10 times faster than the first low-fidelity model, or provides a speed up of 10,000, of 100,000, sorry. What we see is that even though we have the second model that is computationally cheap to evaluate, it doesn't actually do much in reducing the variance further, because we already have a very good first low-fidelity model. And if we add the third one with the same correlation coefficient as before, and it's 1,000,000 times faster, it provides a tiny, tiny theoretical improvement in the mean squared error, but not significant. So this highlights the fact that in this approach, there are other approaches, and I'm not for sure doing justice to all the approaches that have been developed over the past 10 years. This approach, where we have hierarchy of models, if you have one that is quite good in terms of correlation coefficients and speed ups that it provides, it can be quite difficult to gain something more by adding more models. And also, if you're in the situation where your high-fidelity model is very expensive, so let's say it costs hundreds of thousands, millions of compute hours for a single run, where ideally these methods would be useful. You have a low-fidelity model that is very cheap, then you can get substantial speedups. All right. Any questions here? Yes.
This might be a silly question. Just want to confirm. So this multi-fidelity approach helps the variance estimation, but does not help too much of a mean estimation.
It doesn't help what?
Mean, the average. Does it also speed up the
So it speeds up the mean estimation, yes. It reduces the variance of the Monte Carlo estimator for the mean. So the mean squared error of the Monte Carlo estimator is the variance over the number of samples. So the rate stays the same, we don't change that, but we decrease the constant in front of the rate. So we get exactly this situation as Jeff was showing on the first day. So we get a similar rate of convergence, but faster. The constant can decrease quite substantially. which again is to say that for the same budget, you'll get more accurate results, as we see here. Or if you target a similar accuracy, you'll need a lower budget. Yeah. All right, so let's see this in action. So we have done some work a few years ago with Frank, with Ben Persdorfer, who's also a main organizer of the event, and with Julia Conrad, who at the time was an undergraduate student with me. So this was, part of this work was actually her undergraduate thesis back in Munich a while ago, where our goal was to investigate data-driven low-fidelity models for more complex applications, and we took an example focused on turbulence suppression with energetic ions in tokamaks. And we wanted to see, how much potential speed up we can get. So essentially the plots that I showed you before, but this time in an actual application, by using low-fidelity models together with the high-fidelity model, which is a gyrokinetic simulation code. So briefly about the setup, I don't want to insist on this too much. This is me trying to bridge, the two sort of sets of people that are in the room, showing you multi-fidelity method results in plasma physics relevant applications. So this was the parameter set that Alessandro gave us, Alessandro Di Siena, based on a jet discharge that he was studying before. The high-fidelity simulations were performed using Gene. So these are micro-instability simulations. Undergrad thesis project is 3 months, so we had to be considerate that Julia has to graduate and don't do nonlinear simulations. So this was the case with 5 species, model species, deuterium ions, electrons, 2 fast ions, and also impurities. We consider that 14 of the input parameters in the model are uncertain, so most of them characterizing 4 of the 5 species and 2 the geometry. And the quantity of interest here was simply the growth rate of the most unstable mode. And in the sense of uncertainty propagation that we discussed so far, what we wanted to do was to propagate the uncertainty in these 4 input parameters that we consider to be uncertain. And our goal was then to estimate the expected value of the growth rate given the uncertainty in these 14 parameters using Monte Carlo estimators. And without going into details here, because that this warrants a separate discussion, but for the purposes of Monte Carlo, multi-fidelity Monte Carlo sampling is not necessarily that important, we had a hierarchy of 4 models. The high-fidelity model given by Gene, which relative to the other models was more costly. Then we had 3 low-fidelity models, all data-driven, all constructed using the same method. And what we exploited here was the fact that even though we have 14 input parameters, the effective dimension of the problem is lower. So we have considered data-driven models that have all 14 parameters, and then we reduce the dimension from 14 to 9 and then down to 6. We see a table here with the correlation coefficients and the speed-ups that we get with our models, and we see that the correlation coefficients stay high, and we also, of course, get speed-ups by using the data-driven low-fidelity models. And when we plug this into the multi-fidelity Monte Carlo algorithm and compare this with the standard Monte Carlo algorithm that uses just Gene to estimate the mean, so on the left, I show you the theoretical plots, what I showed you before, which is to say that we estimate the quantities that we need to compute the mean squared errors, and then we plug those into the analytical formulas. We don't need any simulations for that, we just need some numbers. On the right, I show you the actual estimated mean squared error computed using numerical experiments. And we compare the standard Monte Carlo estimator that uses just the high-fidelity model, a bi-fidelity Monte Carlo estimator that uses the high-fidelity model and the 14-dimensional low-fidelity model, and a multi-fidelity Monte Carlo estimator that uses all 4 models in the hierarchy. So what we observe is that we get speed-ups, so roughly 2 orders of magnitude in the mean squared error by using the multi-fidelity Monte Carlo estimator, which of course means that we can obtain variance reduction with these data-driven models in this application. So question that should arise is, so as we mentioned yesterday, this algorithm assumes that we have available the correlation coefficients and the evaluation costs of the low-fidelity models. To estimate the correlation coefficients, we need high-fidelity model evaluations, and those cost something. Then the question becomes, do we just throw those samples away because in very complex applications we cannot afford to do too many of these in the first place? So then we wanted to see, at least empirically, what happens if we are reusing these samples that we use to compute the correlation coefficients in the multi-fidelity algorithm itself. So theoretically, we know that this will introduce a bias in the algorithm, but we wanted to see specifically in this application how much that bias will play a role. So we redid the estimations. So theoretical plot on the left, actual numerical simulation plot on the right. And what we notice is that indeed this introduces a small bias, but it is negligible in this application. And in any further application that we did using this strategy, we notice similar results in the sense that the bias that this introduces is quite small. And this makes sense because if you have a hierarchy of models that, for which the multi-fidelity algorithm prescribes a small number of samples for the high-fidelity model, it's unlikely that the bias will play an important role. If, however, you have bad low-fidelity models from the point of view of multi-fidelity Monte Carlo sampling and you need a ton of samples for the high-fidelity model estimator, then that bias will be more significant. I wanted to show this nonetheless because this is quite important in practice. So in practice, we cannot afford to do simulations and throw them away because if you have a large-scale application, then of course maybe you can afford 20 simulations in total and then you want to use them the best you can. All right, so the summary of this algorithm. So the standard multi-fidelity Monte Carlo algorithm developed roughly 10 years ago, exploits hierarchies of high and low fidelity models. The low fidelity models are characterized primarily by two quantities, and this is important for the rest of the presentation. So their correlation with the high fidelity model and their evaluation cost. Using the high fidelity model ensures that the Monte Carlo estimator is unbiased. And the low-fidelity models, which are biased relative to the high-fidelity model, are used to reduce variance. And as we saw in a few examples, having multiple low-fidelity models with heterogeneous properties, meaning correlations and evaluation costs, can further improve efficiency. So to summarize this with a punchline, standard multi-fidelity Monte Carlo sampling correlations and lower evaluation costs are all you need. All right, any questions before we move on? Now we move on to the good stuff. All right, so we have this algorithm that, we are given models, we compute some quantities, and then we work out the math, and we find, the optimal way relative to, this fixed hierarchy of dividing effort among models to obtain variance reduction. However, it's an important detail. This algorithm, it is assumed that the low-fidelity models are fixed and readily available, so someone gives them to us. Now, that assumption, of course, makes sense if the low-fidelity models are, let's say, reduced physics models, which you probably work out on a piece of paper and then you implement the code that simulates them, but not necessarily so for something like data-driven models. So the question is, what if low-fidelity models can be tuned, adapted, refined? So this definitely is the case for data-driven models, but also for others. And the question becomes, how accurate must this model be to be most useful within multi-fidelity Monte Carlo sampling? Which is to say, if you want to use a neural network, the eternal question for this for a while will be, how much training data do I need? And if you just, guess that, of course, you can train the network, compute the correlation coefficient, and use this algorithm. But it would be really great if you would know how much training data you would need to construct a low-fidelity model to be useful within this algorithm. This is what I'm going to show you next. Now, I'm going to show you, so we'll revisit this example because I have, so I looked into the folder where I did these experiments. It was 3 years ago, so I'm thinking to revisit it and maybe actually finish the project. So I have a student now we're looking into this. The idea was to look into, so when you do gyrokinetic simulations, one of the things that you have to deal with is to do these so-called convergence studies where you figure out what's the resolution that you want to use. These can take a while, and take a while to figure out what resolution you need when you use, let's say, Eulerian codes. So my idea at the time was, let's say I'm willing to pay the price, for a high-fidelity model that needs a high resolution. Can I find optimal ways to decrease the resolution to obtain low-fidelity models that are useful for multi-fidelity Monte Carlo sampling? Because that from theory alone is quite difficult to find, as we know when you deal with something like turbulence, coarsening the grid in certain direction can lead to non-physical results. So I did this experiment a while ago where I revisited this case, so the jet case that I showed you before, that had, so this is a linear flux tube simulation with a relatively low resolution. And let's say that we want to decrease the resolution in the mu direction, so the last number, the 16. And let's consider the following two experiments. So assume we are using standard Monte Carlo estimator estimation. So as we showed on the previous set of results. And let's say that I want to use a bi-fidelity Monte Carlo estimator where the low-fidelity model is a coarse grid model that instead of using 16 collocation points in the mu direction, uses either 3, 8, or 12. 8 or 12 probably something that you could consider, but 3 points is kind of too low. I don't think anyone will actually use 3 points for a high-fidelity simulation. So I want to see what happens, with this. So this is a point that I want to make, which will be relevant for the remainder of the presentation. So unfortunately, I don't have actual numerical results with this. I just have the theoretical results. So we are working on this with a student, as I said. But let's say that I want to see what happens. So how much variance reduction do I get if I'm using this bi-fidelity Monte Carlo estimator, where the low-fidelity model is a coarser grid version where I decrease the resolution in the mu direction from 16 points to 3 points. But 3 is extremely low. Correlation coefficient here is 0.93, so it's so and so for multi-fidelity methods. And I do notice that I get some potential variance reduction, not significant because the speed up that I get with the coarse grid model is not as significant as I would get with the data-driven model. But I do get some. Now my question to you is, in the next slide I will show you the results where instead of using 3 points in the mu direction, I use 8 points in the mu direction, which is probably more realistic. Now the question is, knowing that it is likely that I will get more accurate results with 8 points in the mu direction, do you think I will get more variance reduction with that bi-fidelity model or less? So who votes that I will get more variance reduction? Okay, and who votes that I will get less? Okay. So we get less variance reduction. So this is where things start to be a bit counterintuitive, and that's one of the powers of multi-fidelity Monte Carlo methods for sampling. So indeed, if I do a bi-fidelity setting where I have a low-fidelity model that is more accurate, both from a physics perspective but also correlation coefficient-wise, so correlation coefficient is 0.99. I actually get worse results.
So what is the x-axis?
Oh, sorry, that's cut off. So that's the budget.
So in this case, I guess when you increase the n mu from 4 to 8, so in each round, actually, the budget actually increases a lot.
Sorry?
In each experiment, when you increase the number of collocation points from 3 to 8, or
yes.
So in each one, actually, the computational
so the computational budget is the same in all experiments. What I change is just the setup for the low-fidelity model. So the budget will be the budget for Monte Carlo sampling. So I assume I'm given these models, I have their correlation coefficients and costs. So you should have asked what is the cost, because that's really the point here. Because I will make the point in a minute, but so the setup is the same. I'm comparing apples to apples here. There's nothing that I'm doing to favor the model with 3 points in mu. So yeah, sorry, this was cut. Is the computational budget here.
So this computational budget is you're running this low-fidelity model for half.
So this will be the budget that for which I use the high and low-fidelity model to estimate the mean. So this is the online budget for mean computations, for sampling. And this is the theoretical mean squared error, so they see they are parallel to each other, as they should, but one is lower than the other because I get variance reduction. So when I use 8 points, I get less variance reduction. So what do you think now will happen when I use 12 points in mu? So it's 0.25 reduction, 25%.
What are the weights again?
So we get a very high correlation coefficient, but we get almost no variance reduction. So now your intuition probably says, okay, this doesn't really make sense because I'm used to think that if I have an accurate model, that should give me better results. That's certainly true in single fidelity settings, not in multi-fidelity settings. Why? So the question is, and I will actually show, we have theory that shows this. Can low fidelity models be too accurate for multi-fidelity Monte Carlo sampling? Yes. Almost. But the cost is really the key to this answer. So this is the question we'll try to answer next. So recall that in standard way of thinking, which is most of the research, we build surrogates with the goals of replacing the high-fidelity model. So the main driver of this is the accuracy. So we aim to have an accurate model that we can trust, of course, assuming we trust the high-fidelity model in the first place. If that's not the case, then this doesn't make sense. However, at least in multi-fidelity uncertainty propagation, so what we are discussing here, low-fidelity models are not intended to replace the high-fidelity model. So they are characterized by two important components. One is the correlation, the other is the evaluation cost relative to the high-fidelity model. And the goal is to achieve variance reduction. So what I showed you previously, I only showed you the correlation coefficients. I didn't show you the cost reduction. And that's actually key. Because both need to be in a certain value to obtain, variance reduction. So the question is, how much effort do we need to construct low-fidelity models to be effective for multi-fidelity uncertainty propagation? It's a paper that we have done 3 years ago with a similar subset of people from the other one, so with Ben again and also with Frank and my mentors in Germany. This was published in Computer Methods in Applied Mechanics and Engineering. So in that paper, so I gave you the example with the cos-read model to try to build intuition and also had the results for that, so the actual numbers. But the way we've constructed this method was for low-fidelity models that are constructed from high-fidelity model evaluations. So with a bit of a slight change, the same algorithm can also be used for cos-read models. But let's think about low-fidelity models that need high-fidelity data, so data-driven models, for example. And to explicitly denote that we need a certain number of high-fidelity model evaluations to train these models, we'll use a subscript Ni for a low-fidelity model to denote that we need Ni high-fidelity model evaluations. So what's the summary in words of this? So for those of you who missed yesterday's presentation, I have a slide where I put everything in words and then I show you the math. So, depending on your cup of tea. So a summary of this, if I were, to do a presentation where I don't show any formulas, is something like this. So previously, we assumed that the models are fixed. And what does it mean in the multi-fidelity Monte Carlo setting? That their correlation coefficients and evaluation costs are fixed and given. Now, if we understand how the correlation with the high-fidelity model and evaluation cost change as the training size increases, so we have a, if you want, a dynamic behavior of these models, if you want, then what we can do by working out, a bit of math, we show that we can optimally balance the training of the low-fidelity models and using them for sampling within multi-fidelity Monte Carlo. And this is done by minimizing an upper bound of the mean squared error. I will show you some details here, so the math is not necessarily complicated, but it requires a lot more slides that I have to explain properly. So this is a quasi-optimal algorithm in the sense that we are doing the minimization with respect to an upper bound. But nonetheless, we have shown that we can do this, and we also have some theory that shows that under certain assumptions, these minimizers have certain important properties that I will mention in a minute. So what you noticed in the previous slide is that, so this balance has a sweet spot, which says that beyond a certain point, further improving the low-fidelity model in a classical sense, so aiming only accuracy, can actually be detrimental for the multi-fidelity Monte Carlo estimator. All right. So we are calling this thing context-aware learning of low-fidelity models for multi-fidelity Monte Carlo sampling. And a quintessential example, as I said, is for data-driven models that require high-fidelity model evaluations. And what's the gist of it? So the idea is that we have low-fidelity models that we use in a multi-fidelity hierarchy to estimate means, so to do uncertainty propagation in this example. And the important details that I alluded to previously was that these models play a role in, within a framework that incorporates other models as well. So we don't judge them individually, but rather how they interact with other models. And also, importantly, the target here is to estimate the mean. So we have an outer loop result. So all models predict the same quantity of interest, but overall, their goal is to effectively estimate the mean of the high-fidelity model together. All right. So as I said, we need to consider how correlations and evaluation costs change as the training size varies. So instead of assuming that they are fixed as before, now we assume that we have rate functions that tell us how this, coefficient, the correlation and the evaluation cost changes. So in more details, we assume that we have a rate function that tells us how fast 1 minus the correlation coefficient squared decreases. And we assume that in this framework, this decrease is monotonic, which there are situations where this doesn't happen. But for the purpose of this discussion, we assume this. And we also assume that we have a function that tells us how fast the evaluation cost of the low-fidelity model increases as we increase the training size. So the evaluation cost of a low-fidelity model will increase, for example, when we are in a reduced order modeling setting. When we increase the size of the model, we'll also increase its evaluation cost. This can also stay constant. So for example, I have a neural network that is fixed. So the architecture is fixed. If you change the training size, the training time will increase itself, but the evaluation time of the network will stay more or less constant. So what we care about here is the evaluation time of the model, because this is the important ingredient for multi-fidelity Monte Carlo sampling. Yes?
Do we assume what kind of learning model we are using to target this specific problem, or no? It's like nice statistical learning model. You can describe how generalization looks like, then maybe you can get a really analytical thing on this.
So
increasing of the correlation, increasing of correlation.
So are you asking whether we assume certain expressions for these rates, essentially?
Yes and no. Yes, it's because I think if we assume some statistical learning model, then maybe this can be derived, I guess, with your, because you can bound the generalization error. In that case, you can bound
in this case, the way we think about this is the following. For many models, you have some theory. In model reduction, at least for linear models, you have. In some others, you have no theory.
Yeah.
So if you have theory, you know these rates. You probably know the expressions, maybe you don't know the constants. If you are lucky, maybe you also know the constants. For some, you don't. If you don't, and I will show you examples with this, you estimate them from pilot runs. So if you have some a priori knowledge about the accuracy and cost of your models, you can use this for sure, but otherwise you can estimate this from pilot runs. Yeah, so the framework does not make any will make some assumptions in the theory, which actually I'm not showing here, for the sake of doing a generalized theory. But in practice, what happened in everything that I've done with this method is that as long as these rates are sort of monotonic, then everything pretty much works out. So if you don't have it, you can estimate it numerically.
Mm-hmm. maybe there is a class of kind of learning functions that's gonna have, like, gonna satisfy this accuracy rate function you have. Because
So the
you have found the tail, right? If the tail is too bad, then maybe
Yeah, or
you're
if you
not able
have,
to
I don't
found
know,
the real skill.
bifurcation in your parameter set and whatnot, you don't have a monotonic behavior, then this would have to change. But we are assuming essentially that as you increase the training size, the accuracy measured in terms of correlation coefficients improves. Yeah. All right, so let's revisit the Monte Carlo, multi-fidelity Monte Carlo estimator, and it's the same as before, but now I'm explicitly using these subscripts n1 to nk to denote the fact that now the low-fidelity models that enter essentially in the sum depend on, they are trained using or constructed using n1 to nk high-fidelity model evaluations. So now I'm rewriting the mean squared error of this estimator. So we had the expression before, which was the product between the mean squared error of a single model with the variance reduction factor that depended on correlation coefficients and evaluation costs. And now this expression became a bit more complicated because I'm explicitly denoting the fact that the correlation coefficients and evaluation costs depend on these n1 to nk numbers. So these things will change as n1 to nk changes. And also, if you look carefully, the denominator is no longer p, the budget, but rather is p minus the summation of these ny's. Why? Because in this algorithm, I want to do something like an offline-online decomposition, where offline, I want to construct my models. So I'm given a budget. I want to use part of that budget to construct the models, and then I use the remainder of the budget for multi-fidelity Monte Carlo sampling. So I'm accounting for the construction cost explicitly here. And the goal, of course, boils down to finding the optimal numbers of these n1 to nk values that explicitly target minimizing this mean squared error. So the way of thinking here, which kind of departs from single fidelity approach, is that we have an outer loop result in mind, which is a mean estimation. And our goal is to minimize this mean squared error. So we want to find the n such that, when we put all models together, this is what they achieve. So we don't target standard accuracy, which would be useful if we would target to replace the high-fidelity model, but rather we target the fact that we are using them together to reduce variance. Now I'm skipping a few slides of formulas here to show you the end result, but the math is actually pretty simple. It's just a few inequalities that you have to apply. So what we want to do is to start from the expression of the mean squared error and use the fact that we have these rates available. So we assume that we have them available to find an upper bound of the mean squared error that depends on the rates. So I want to exploit the fact that I have the rates and use them for a minimization problem eventually. So if you apply two inequalities, basically, you will obtain that an upper bound of the mean squared error depends on a quantity that, so we call this kappa I minus 1, that essentially depends on the rates of the first k minus 1 models, plus another term that depends on nk only, which is more or less the summation of the accuracy and cost rate of the kth model, where the constant in front for the accuracy slightly changed. This in itself is not important. The important thing is that A, we have an upper bound that depends on the rates, which can be obtained easily by working out, applying two inequalities. And also, another important aspect here is that we have this sequential structure built in, where, inductively, the previous k minus 1 steps are separated from the current step, the kth step. In the first version of the slides, I had all the math put here, but then I thought, maybe this would be too much and it will take too much time. So if you want to have a look at this in more detail, have a look at the paper. What are the key insights here? So no further formulas, just words. So as I said, this upper bound has two additive parts. One that depends on the first k minus 1 models. So think of this k as varying from 1 to a certain number. And one depends on nk, which tells us that we can sequentially add models into this framework. So we can start by adding one low-fidelity model, then we add a second one and the third one sequentially. which made the analysis for this quite, simplified this quite tremendously. And also, you have to take my word on this, so we have theory that shows that this is the case. So we can show that under certain assumptions, we can prove that the minimizer, so essentially the n that minimizes this upper bound of the mean squared error, exists, is unique, and importantly, is bounded independently of the computational budget. So what does this mean? This means that as you increase your computational budget, so in single fidelity settings, you will kind of assume that the amount of effort that I need to achieve a target accuracy will likely increase. Maybe at some point I reach, the desired level of accuracy, but that the training size will likely increase quite a lot. What happens here is that when we increase the budget, this optimal number of samples that I need to construct my low-fidelity models will saturate, which means that beyond that point, if I would increase that further, this is when I will get worse results in my mean squared error. Because I will gain in accuracy, but the cost of the model will increase. And that's where things will not be in balance anymore. Yes? Sorry? So we can talk afterwards. It's a bit more detailed. Sorry? Yes, so in the case where the rates are algebraic, so meaning that the accuracy decreases like n to minus alpha, the cost increases as n to beta. You don't have to make any assumption. The theory is very solid. So there is a paper on that. In this paper, we wanted to do the generics approach, where we assume we have the rates, but we don't assume that much about the rates. And that's mathematically is not necessarily complicated, but when you work with the generic quantity, you need to put some assumptions to make the math work. So we have some, but empirically we noticed that the theory holds in more or less all cases. Yes.
Is this bounded independent of computational budget also basically an implicit argument that you don't need to include the cost of training in your analysis because it's just a constant?
So the cost of training is introduced here. So we have it is essentially this guy here. So this is to say that you don't need to train your models indefinitely.
I was interpreting that as NI is like the cost to run a model.
So that's the NI is the number of high fidelity model evaluations that you use to train the low fidelity model.
Okay, but that doesn't include like the time to train it.
No.
That's what I was asking.
Yeah. So that we don't take this into account explicitly, which of course would make the use of things that take days to train quite difficult. So you need humongous budgets. So we don't take that into account, just the high fidelity cost. Yes?
So you were saying that with the ratio of how fast you are and how accurate you are, you can say if it's going to help or not. Can you draw some ISO lines to tell people, if you have a correlation of that much, your budget should not be more than 80% of the original cost or something?
So if you give me the rates, I will give you the exact number. But I need the rates. I will show examples with this. Yeah.
So here, I mean, like you have I equals 1 to k. You mean like you're gonna add every time you're gonna add a new low fidelity model to this?
Mm-hmm.
Or I have a neural network. I just add more training data to train the same neural network.
No. So you train the network, fix the training size, and you add either another network, which probably will be not add much, or add another model. So not continuously refine a model. So NI, once it's fixed, is fixed. Yeah. We are working now on an extension where we'll do this adaptivity, but that's not in this particular framework. So take your network, you assume you know the rates, train the network, put it here, and then you add another model if you want. Possibly. That will be probably not add much information. It will probably have to be a different type of model. Right, so the implication of the last thing is that these low fidelity models can be too accurate. And this is very much in contrast to standard model reduction. So again, in model reduction, we target accuracy. Of course, cost is important, but the main driver is accuracy. Here, both accuracy and cost are important. That's really the punchline. All right, so what's the procedure for doing this? So assuming we have these rates, we form an upper bound, we minimize that upper bound. So we start with one model because, as we saw on the previous slide, we have this sequential structure. So we start by adding one model, then we find this quasi-optimal number of training samples for the first model. Why I say quasi-optimal? Because it's with respect to an upper bound. Assemble the estimator, and the second model, optimize for that, and repeat up to the point where essentially you don't get further variance reduction. And then we have this quasi-optimal training sample size for the K models, and after that we use these models online for multi-fidelity Monte Carlo sampling. And to a certain extent, this is similar to the concept of exploration versus exploitation in Bayesian optimization, and John and collaborators have papers in this direction in multi-fidelity Monte Carlo sampling, where they approach this from a different perspective. So this balancing of explorations versus exploitation. All right, let's see some examples. So let's start with an academic example focused on heat conduction in a two-dimensional spatial domain, where we have d equals 9 uncertain inputs. So this is a 9-dimensional problem from the point of view of uncertainty propagation. So step by something like this. The high-fidelity model is a heat diffusion equation, static, so it's elliptic. That will be important for further on, where the domain is partitioned into a 3x3 tile, and then the heat conductivity essentially is piecewise constant here. So we have a constant heat conductivity in each subdomain. And then the quantity of interest is the mean temperature on the bottom boundary of the domain, which is a Neumann boundary. The right boundary is also Neumann, and then the top one is Dirichlet. So it's well-studied example in the reduced spaces community and other places. So this model is implemented using finite elements. It's relatively small, fast to evaluate. So this was, of course, used for us to showcase the properties, the theory that we derived, and also to understand a bit better practically what happens with the context-aware multi-fidelity Monte Carlo estimator. So in our experiments, we consider two low-fidelity models with heterogeneous properties. So here, what I mean by that is our heterogeneous rates. So because it's an elliptic problem, the first low-fidelity model that we considered is based on the reduced basis method. So for those of you who are familiar with model reduction, you know what this means. For those of you who are not, the reduced basis method is essentially will provide extremely accurate surrogate models for this type of problem. So for elliptic problems with the reduced basis method, you get exponentially accurate models. So this is based on an offline online decomposition. The implementation is provided in this library, but the thing to keep in mind is that you have an exponentially accurate model. And the second one is a data-driven model based on epsilon support vector regression that we chose. So we chose this epsilon, which is a degree of freedom, in such a way that this model is not necessarily very accurate, but it's a lot cheaper to evaluate than the reduced basis model. So when you do reduced basis online, when you query the reduced order model, you have to solve a dense system of linear equations of size r by r. So that's more costly than querying the data-driven model, which is very cheap to evaluate. So we have two models, one that is very accurate but more costly to evaluate, and the second model that is a lot cheaper to evaluate but less accurate. So we know theoretically that the reduced basis method will give us an exponentially accurate low-fidelity model. We know the rate function, we don't know the constants. So we estimated those from pilot runs. And we indeed noticed that 1 minus the correlation coefficient squared decreases exponentially as I increase the training size, so I increase the number of reduced bases. And then when I evaluated this on my machine at the time, so the estimation of the cost, this increased roughly linearly up to 100 reduced bases. And now we check this outrageous claim that low-fidelity models can be too accurate, which theoretically this means that the optimal number of reduced bases should saturate and bound as the budget increases. And this is indeed the case. So if we are computing this N1 star optimal as we vary the budget from 5 to 500 seconds, the upper bound of this is 18. So which means that with respect to the upper bound that we have considered and the rates that we have, we need at most 18 reduced bases to construct a low-fidelity model in our setting. And on the right, I show you how the budget evolves offline versus online. So offline, I mean the N1 samples that I need to construct the low-fidelity model, and then online meaning what I use for sampling. And as we expect, as we increase the budget, most of it will actually be used for online computations because N1 star bounds. And to see this concept of replicating what we have seen in the case with the coarse-field model for the jet example, so what it means that low-fidelity models can be too accurate. What I'm showing here is the comparison between the standard Monte Carlo estimator, the multi-fidelity Monte Carlo estimator, with a fixed number of bases in the low-fidelity model, so something that I would do with the standard method where I assume that someone gives me that model. And then the result with our context-aware version where we use this quasi-optimal number of bases to construct the model. On the left, as before, I show you the theoretical plot, so the theoretical estimates of the mean squared error. On the right, results obtained from computations. And then, so we see, of course, that all multi-fidelity variants outperform the standard Monte Carlo estimator by, at the end, by quite a lot. In the standard static multi-fidelity Monte Carlo estimator, I have considered that I use 2 reduced bases to construct the low-fidelity model, which doesn't give rise to a necessarily very accurate low-fidelity model. We can see this reflected in the results. 8 reduced bases, so this decreases the variance, and then 50 reduced bases, which gives rise to an extremely accurate low-fidelity model that is almost, has a correlation coefficient of 0.99999. However, that model with 50 reduced bases, which intuitively you would say, okay, because this is so accurate, it should be useful for multi-fidelity Monte Carlo sampling. It turns out that actually gives rise to a larger mean squared error than our context-aware reduced bases model with 18 bases. Because the accuracy cost ratio for the 18 reduced bases low-fidelity model is actually optimal with respect to this upper bound. All right, so let's add also the second model into the loop. So we have this less accurate model that is data-driven, data fit-based, so very accurate very cheap to evaluate, but less accurate. So this one has an algebraic rate that it decays quite slowly as the training size increases because we chose that epsilon to be rather large. However, what we notice is that even though this model by itself is not necessarily very accurate, probably you'll not use it to replace the high-fidelity model unless you have a very large training size. It gives rise to further variance reductions. If you look at the dark blue line, it's not tremendous, of course, it's still a relatively simple example, but it gives rise to further variance reduction. All right, and then here we show the sample distribution among the 3 models. So this is the last setting where we have the high-fidelity model, the reduced bases, and the epsilon SVR. And then we see, for different estimators, so from standard Monte Carlo estimator to the static multi-fidelity Monte Carlo estimators to our context-aware variants, we see the sample distribution. So from the total of samples that the budget permits, so the MK samples, we see that what happens in the multi-fidelity estimators that more than 99.9% of the samples are allocated to the low-fidelity models, whereas a small percentage is used by the high-fidelity model, which is what we want. So we don't want to query the high-fidelity model too many times. All right, so should probably speed up. I also have results for a plasma problem with this algorithm. Probably go through it quite quickly. Because now you saw what happens, how this idea of low-fidelity models can be too accurate manifests here. So we had a case at the time when we did the paper. So the paper was a methodological paper, but we wanted to show this also in a more, in a non-academic example. So this was a case based on Aztecs that I had from my PhD. So this was, again, plasma micro-instability simulation, where we had this resolution, 2 model species, and the quantity of interest, again, was the growth rate of the dominant micro-instability mode. And this was, for the purposes of authority propagation, a 12-dimensional case. So we had 12 parameters that varied. We have considered 4 four models in our hierarchy, sorry. So the high-fidelity model is given by Gene, so plasma micro-instability simulations with Gene. We had also considered a coarse read model because we wanted to show that even though the algorithm is designed for models that can be, that can be constructed from data dynamically, we can also incorporate static models, so there's nothing that stops us from doing that. So the second model in the hierarchy is a coarse read Gene model, where we construct the grid in certain directions. The second one, the third model, the second low-fidelity model is a sparse read model, similar to what I showed you in the JET case. And the fourth one was a neural network. So designed to be quite, inaccurate on its own, but we wanted to make the point that even this inaccurate model can still be useful in a multi-fidelity setting. So something extremely, extremely simple. So we evaluated the rates of our models. So we got algebraic rates for for the two data-driven models. So we designed the network in such a way that it, as I said, is not necessarily very accurate on its own, but as I will show, it will be useful. Then we have done the following experiments. So bi-fidelity setting with the coarse read Gene model, bi-fidelity setting with the context-aware sparse read model, three models where one is the coarse read model, and the second low-fidelity model is the sparse read model, and then a fourth example where we have the coarse read model and the deep neural network model. So let me show you this example. So we have done these experiments only for one budget. So I don't have the plot that shows the decay of the mean squared error for increasing budgets. We have done just for one. But what I'm showing you here is the estimated mean squared error from numerical experiments, comparing the estimators that I just mentioned. And what we can observe is that when we move to the estimators that include the context-aware data-driven models, we decrease the variance by roughly 2 orders of magnitude. So even using, for example, the deep network model that on its own is not necessarily very useful, in this multi-fidelity setting, it can lead to substantial variance reduction. And again, on the right, I showed the distribution of samples among all models. All right. So the summary of this is that this context-aware extension trades off training hierarchies of low-fidelity models with Monte Carlo estimation. Our theory shows that low-fidelity models can be overtrained for multi-fidelity purposes, which is good news, especially for fusion energy research, because if you want to use this for a very complex application, maybe you get away with a model that is not trained from a large data set. And data-driven models trained from small data sets can be useful. All right, any questions here before we wrap up? Yes. It was pretty poor, so pretty poor from what we typically use in multi-fidelity models. So I think it had a correlation coefficient of, I have to double check the numbers, but 0.9 or less, which, it's good or not. Yeah.
So the overtraining happens as the overtraining is a balance between the computational cost of running inference on your low-fidelity model, right? So this is a key thing.
Yeah.
So empirically, have you seen cases where even when you have, for example, a low-fidelity model that runs, a billion times faster, we get these ridiculous numbers with, feed-forward neural networks compared to gyro codes or something. Even when it's a billion times faster, do you still see instances where there's overtraining?
So,
a reasonable correlation code.
If it's a billion times faster, for you to observe the overtraining, you'll need relatively large training size. So you cannot really see this in this plot, unfortunately, but what happens here, so I didn't want to get into this, but it's quite important. So if you look closely to the dark blue line, you'll see that it decays a bit faster than 1 over n. What happens in context-aware multi-fidelity estimators is that pre-asymptotically, actually, you get exponentially fast decay. And then when essentially this happens when the low-fidelity model cost relative to the high-fidelity model is 0 or close to 0. So pre-asymptotic, actually, we get faster decay of the mean squared error, and then the bias kicks in, and then the variance starts to matter, and then you start going to this normal rate. So if you have something that is extremely cheap, then this overtraining, to see it, you'll need a very large training size. Because to balance, the accuracy to the cost, you'll need a relatively large training size. So I was hoping to show you an example here again, theoretically, from a more expensive model, and I have seen this in something that it's essentially 1 billion times faster to evaluate. Not with a network, but with an interpolant. But yes, so this can happen. And of course, if you are using this N1 star, you'll get the optimal results with our algorithm. But if you cannot afford N1 star, but you can afford N1 star minus 10, you still get good results. Not quasi-optimal, but you still get some decent results. Yes?
So when you train the neural network, you have a neural network model.
Mm-hmm.
Do you only train it with N2, or you also use N1 samples together to train it?
So do I only train it how?
Only use the N2 samples to train it, or you also include N1?
So I only use N2, yes. So N2 is the number for...
Is there any consideration you don't want to put N1 also in the training for a neural network? Because in my opinion, it seems like more samples should give you better result. And anyway, this N1 already exists here.
You could do that.
So
Yeah.
do you think this is going to kind of break your correlation structure, or no? It's not going to? Because it seems like your multi-fidelity modeling approach seems the model are using independent data or kind of like independent data.
No, you can, if you have them available.
Uh-huh.
So
It seems like this
everything
is
will
a natural
improve the
approach, right?
results.
If you have something already there.
Yeah. So I haven't done this, but that's a good point. Yeah.
I just want to say this is a really good point because this is something we do all the time. Like we usually have medium levels of fidelity of like multiple levels of fidelity from the numerical models, and we'll use the data weighted differently to train different the same neural network as a as a surrogate of all of the levels. So you can like pre-train on your medium fidelity data, which you might have a lot of, and then fine-tune on your high fidelity data, which you only have like 5 of. It'd be really interesting to like propagate this through through this framework to see like where it ends up.
So here the assumption is that I use only high fidelity samples to train, but yes, you can include that.
Yeah.
Just have to account this properly in that budget.
Yeah, I'm saying we should do this like in the we should do the math. Yeah.
All right. Any other questions? All right. So I had more slides about this, but because Boris did such a fantastic job yesterday to talk about design, I took away all my slides about multi-fidelity design optimization, which is probably a good idea because I only have a few minutes left. I will keep this rather vague and generic because I think this is one of the spaces where multi-fidelity methods can really be beneficial for fusion research. Not to say that search propagation is not. I mean, it can be extremely and should be used. So I don't think we should do deterministic simulations. But there is rather mature. So we have a lot of methods that are quite powerful, and I think, at least from the point of view of outer loop applications, probably the most development was done in that space. But I think when thinking about design optimization and ultimately plasma control, I think multi-fidelity methods can really play an important role. Let's not go in further details here because we will discuss this in the 4th workshop, but just I wanted to mention this here, and I think this is a space where we can, over the next 3 months, discuss all together and see from what exists, what can be useful, and what will need to be further developed to make this multi-fidelity methods really meaningful, for design optimization, control. For control, of course, if we enter the real-time control, this keeping the high-fidelity model into the loop idea probably will not make sense, because if you want real-time control and your high-fidelity model takes a week, then it's not really real-time. But nonetheless, I think multi-fidelity methods can be useful here. So, just a philosophical slide about control here. So, some ways in which this can be used is, for example, to leverage reduced models or learned models for fast predictions. So periodically correct them using higher fidelity data, like from experiments, for example. or combine physics-based and data-driven models. And of course, there are some approaches based on multi-fidelity learning-based control. So I'm not sure what Ben will talk about in the fourth workshop, or maybe he will talk about some of this work in this space. And there are more, papers coming up in this direction. The point being that, this is a potential area where multi-fidelity methods can be very meaningful for fusion energy research. And we'll talk more about this in the fourth workshop. And lastly, to reiterate what I discussed on Monday, so we mostly talked about multi-fidelity methods for outer loop applications, and they can be extremely useful there. But it's not necessary to use, or it's not, we're not restricted to use multi-fidelity methods and modeling just for that. So they can also be used to, accelerate the underlying high-fidelity computations themselves, for example, which sometimes can be quite meaningful. So examples in this direction include domain decomposition methods, which are the main driver of large-scale simulations based on grids on supercomputers, where instead of aiming to find a reduced model, for example, that is accurate or has a large correlation coefficient everywhere, rather you use a low-fidelity model for a subdomain, and then you keep the high-fidelity model for the subdomain where the dynamics are very complex and are difficult to approximate. Multi-level, multi-resolution methods are also an example, and as Jeff mentioned on Monday, this idea is definitely not new. It's just reused and refined in different communities. And of course, we have these hybrid physics data approaches where we can combine physics-based models with learned surrogates. An example being closure modeling, and I think we'll have a few talks in the workshops focused on this. So the point is, it's not necessary to use or it's not restrictive to use, not restricted to use multi-fidelity methods only for outer loops. So multi-fidelity modeling, I would say, offers tremendous opportunities to accelerate in advanced fusion energy research. This cannot really be done by one community, so we'll have to talk to each other, and this is the goal over the next 3 months. I have a bunch of backup slides. Let me just briefly mention this, so maybe you can start discussions afterwards. So I didn't mention anything about multi-fidelity methods for approximation. So this can be done as well. So methods like multi-fidelity spectral expansions, also known as polynomial chaos expansions, are available in the literature. Multi-level, multi-index stochastic allocation methods. So this sort of following up what John presented 2 days ago. Multi-fidelity Gaussian processes, and so on and so forth. There is a review paper published in 2023 that focuses more on multi-fidelity methods for surrogates, if you want to have a look at this. I also want to mention something that I'm working on at the moment. So I'm doing some work on multi-fidelity data simulation. So we have a project at Virginia Tech where we want to build a digital twin for a jet engine, which is kind of difficult. And data simulation, as you know, for digital twinning is one of the backbones. So data simulation is pretty hard. So as Tim mentioned in his tutorial, there aren't that many methods, multi-fidelity methods for inverse problems. So there is, as far as I know, just one established method that is multi-fidelity for data simulation, and mostly for ensemble Kalman filtering, where the idea is so let's say you want to estimate the state of a system from noisy measurements. You have a model that predicts that state. The model is imperfect, and you want to correct those predictions using data measurements that are most likely sparse. So multi-fidelity methods can help in here because you can leverage low fidelity, cheaper to evaluate surrogate models to estimate, for example, ensemble statistics, while, as we do in multi-fidelity Monte Carlo sampling, you still keep the high fidelity model into the loop for accuracy guarantees. And just to show you an example of some of the stuff that we are doing now, so this is multi-fidelity ensemble Kalman filtering estimation of the state for the two-dimensional quasi-geostrophic model, which for the physics folks, this is similar to the Hasegawa-Katani model. And what I show here is the estimation of the state using the multi-fidelity method in the center. So the reference is on the first column, center multi-fidelity analysis. On the right, we show the analysis using just the high-fidelity model alone. And the number of effective ensemble sizes is the same in the two. So what we see is that with the multi-fidelity method, we can actually get quite decent state estimation. So what we observe in these research is that multi-fidelity methods can play quite an important role in data simulation and digital twinning, and there are also applications for control that are relevant for fusion research. All right, so thank you so much.